This question is about an experiment to measure the wavelength of microwaves. A microwave transmitter T and a receiver R are arranged on a line marked on the bench. A metal sheet M is placed on the marked line perpendicular to the bench surface. Figure 1 shows side and plan views of the arrangement. The circuit connected to T and the ammeter connected to R are only shown in the plan view. Now we've got figure 1 here, which shows a side view of the metal sheet, which is running parallel to some line connecting the microwave receiver and the microwave transmitter. You can see that represented by Y. Now the plan view is a top-down sort of bird's eye view, which shows that plate running alongside that line between R and T. Now it says the distance Y between T and R is recorded. T is switched on and the output from T is adjusted so a reading is produced on the ammeter as shown in figure 2. So we've now closed this switch, so we should start generating waves. M is kept parallel to the marked line and moves slowly away as shown in figure 3. Now you can see in figure 3 there, that plate as described is moved away by a distance x from that line. It says the reading decreases to a minimum reading which is not 0. The perpendicular distance x between the marked line and M is recorded. The ammeter reading depends on the superposition of waves travelling directly to R and other waves that reach R after reflection from M. State the phase difference between the sets of waves superposing at R when the ammeter reading is a minimum. Give a suitable unit with your answer. Now what we should be able to see without even looking at this diagram is that when there is a minimum ammeter reading, there will be a minimum amplitude of this superposed wave. The waves will be arriving at R in antiphase, which means that their displacements will act to oppose each other and create a reduced amplitude of the wave, resulting in a much lower current reading on the ammeter. So the phase difference should be either pi radians or 180 degrees. And you'll get 1 mark for saying either of those things. Explain why the minimum reading is not 0 when the distance x is measured. Now for this scenario, what we can see is that the waves are arriving in antiphase, so they will have a different path to each other. So they will have a path difference of half a wavelength. So let's look back at the diagram. Now, one potential path for the waves to travel along is along that dotted line going from T to R, but an alternate route would be to reflect up at the plate and then back down to R. And as you can see, when traveling from T to M to R, there is a longer path, which means that the waves don't arrive in phase, but they arrive in antiphase, and they should have a path difference of half a wavelength. Now, the waves don't need to cancel each other out entirely. That wave that travels from T to M to R could lose some of its intensity when it's reflected at the metal plate, which means that its displacement at a given time may not fully counteract the displacement of a wave traveling in a straight line. So there will be a reduction in amplitude, but the amplitudes may not oppose each other entirely in both directions. But it's not enough to say that they don't fully cancel each other out, because that's not a sciencey enough way to say that. So we need to mention amplitude and talk about this idea that the combining waves do not have the same amplitude. Now I've added an extra bit of detail there just about the displacements opposing each other but not being the same in magnitude, so they may not fully oppose each other, but to get that mark you only need to mention what's written in black there. So the amplitudes of the waves from the two paths may be different. When M is moved further away, the reading increases to a maximum, then decreases to a minimum. At the first minimum position, a student labels the minimum n equals 1 and records the value of x. The next minimum position is labelled n equals 2 and the new value of x is recorded. Several positions of maxima and minima are produced. Describe a procedure that the student could use to make sure that M is parallel to the marked line before measuring each value of X. You may wish to include a sketch with your answer. Now you'll notice there is a space underneath this question to draw a diagram, or a sketch as they say, and then space to actually explain that answer. So let's first of all draw a sketch of our method, and it's going to involve a set square. Now these two triangles in the middle are the set squares. You'll notice because they both are right-angled triangles, we can align them as shown here, and if they are arranged in such a way with their bases running horizontal, then this plate M and the line between the emitter and the receiver will also be parallel to each other. You'll notice as well that if we slide those set squares up and down past each other, then we can increase and decrease the value of X, i.e. moving M further and closer to the line between the transmitter and the receiver. The other point to add to this is to make sure that M is definitely running parallel would be to measure the distance between the set squares at both ends of M and make sure that those distances between the set squares are the same. So the distance that I'm kind of indicating is this distance of overlap. So for this question, you would get 1 mark for a suitably drawn and suitably labelled diagram, and then a 2nd mark for explaining how to utilise those set squares at both ends of the plate. It can be shown that n lambda is equal to the square root of 4x squared plus y squared, or minus y, where lambda is the wavelength of the microwaves and y is the distance defined in figure 1. The student plots the graph shown in figure 4. The student estimates the uncertainty in each value of the square root of 4x squared plus y squared to be 0.025 meters and adds error bars to the graph. Determine, first of all, the maximum gradient Gmax of a line that passes through all the error bars. And secondly, the minimum gradient Gmin of a line that passes through all the error bars. So let's have a look at the graph. Now we have a set of plotted points here, all with error bars. What we're going to need to do is to plot a line with a gradient Gmin, and that is going to be the shallowest line that we can get while still remaining within all of the error bars on the points. The Gmax line is going to be the steepest line that we can get while remaining within the error bars. So let's draw those. So those are my lines of best fit. As you can see, the steepest one just about fits through the bars, but touches this error bar at the top and this error bar at the bottom. And then the shallowest line just about passes through this error bar here and this error bar here. If we made the steepest line of best fit any steeper, it would fall outside of that point. If we made the shallowest line any shallower, then it would also fall out of one of those purple zones. So let's just label those lines. So your first 2 marks will be for correctly plotting those lines. Your 3rd mark is going to be for correctly calculating the gradients of the 2 lines over acceptable changes in y and changes in x. Now, I would recommend for something like this going over as large a range as possible. So let me just draw the 2 triangles that we're going to need to do. So this is the triangle for Gmax. Now our value has a change of 0.382, which is calculated as 1.617 minus 1.235. Our change in x is going to be 12 because that's just the width of the graph space and it's also the width of that triangle. If we then draw another triangle for Gmin, it's going to overlap with our original triangle, but that doesn't matter too much. We can still find a suitable gradient. Now again, our change in x is going to be 12 because that's just the width of the graph, but our change in the y value is a bit easier to work out this time. It's going to be 1.575 minus 1.275, which is 0.3. So if we write down all of our changes in y and changes in x on the answer space, so calculating the gradients by dividing delta y by delta x in both cases, now we end up with 0.0318 and 0.025. Now, in this scenario, plotting a line of best fit and calculating the gradient is something that you partially have to do by eye, so there will be some margin for error. The mark scheme says to expect 3.21 times 10 to the minus 2 for Gmax and 2.49 times 10 to the minus 2 for Gmin. Now that second one, that Gmin, does round to 0.025, so we're fine there. And it says to expect 3.2. times 10 to the minus 2 for G max, and our 0.0318 does round to 0.032. So our answers are well within that expected range. It's important to make sure that we write down our units as well. Since n doesn't have a unit and the y-axis values are in meters, then by dividing a value in meters by a value without a unit, then we're going to get a value in meters. So those correctly calculated gradients are going to give us our third mark. So 3 marks there. Determine lambda using your results for Gmax and Gmin. Let's first of all write down the unrounded values of Gmax and Gmin. Now we're going to use those shortly, but let's first of all write down the equation that we had in the first place, and we'll see if we can turn that into a straight line equation. Now, according to our graph, the y values, or the values on the y-axis, are the square roots of 4x squared plus y squared values. And on the x-axis, we've got the n values. So aligning this with a straight line equation, we can see that the gradient of this graph represents lambda, and the y-intercept of this graph represents the values of y, which we'll look at later. Now, this doesn't tell the whole story, because whilst we can find lambda from the gradient of the graph, we have two gradients, the most extreme steepest and the most extreme shallowest. So we need to find the average of those two gradients. So add them together and divide the answer by 2, giving us a value of 0.0284, which we can write into the answer space. Now, in terms of marks for this question, it's very unlikely that you'll get the correct answer by doing the incorrect method. So 2 marks will be awarded for getting the answer between quite a narrow range. You'll get 1 mark for getting an answer between a wider range. So because our value is between 2.8 and 2.9 times 10 to the minus 2 meters, we get 2 marks. 1 mark would be awarded for an answer between 2.7 and 3 times 10 to the minus 2. So 2 marks there. Determine the percentage uncertainty in your result for lambda. Now, the first thing to do is calculate the absolute uncertainty in the lambda value, which is how far away one of those two extremes deviates from the true value. So let's write down the value of lambda and use Gmax as an example. So the difference between those two values will be the absolute uncertainty in lambda. So your first mark would be for correctly obtaining that absolute uncertainty. Your second mark would be for correctly using the formula to calculate the percentage uncertainty from the absolute uncertainty. So we would need to divide that 3.4 times 10 to the minus 3 by the original lambda value. So our fraction uncertainty, which doesn't have a unit, will be 0.1197. To express that as a percentage, we need to multiply the value by 100. Now, because this is an uncertainty, it would be best to round it to a whole number. So we end up with 12%. And if our percentage uncertainty is within the range of 11 to 14%, according to the mark scheme, then we get our third mark. So 3 marks there. Explain how the graph in figure 4 can be used to obtain the value of y. You are not required to determine y. So let's first of all go back to the graph and see what we can obtain. Now, what you might remember from this graph is that because we obtain a straight line, we can model the equation for a straight line, which means that the y values that they are asking for, which they're not asking us to obtain, but it's asking us to explain how to calculate those values, is the y-intercept of this graph. Now we have 2 y-intercepts because we have 2 lines. Remember, those are extremes, so the best thing to do would be to find the average of those 2 values, and that would be the average of the line of best fit, or the best line of best fit. So our 2 values are 1.275 and 1.235. Now, as it says here, you're not required to determine y, so we don't actually need those values, but we just need to explain how to find the value. So the first thing to do would be to say, calculate the y-intercept of the graph. And that would be your first mark. The second mark would be for correctly recognizing that there is no clear y-intercept for the best line of best fit, so we need to find the average of the 2 values that we have. And that would be our second mark. So just to show you what that calculation would look like, as we said before, the 2 y values are 1.275 and 1.235. So we would find the mean of those two values and then calculate their mean. So that would be how we make that calculation. Suppose that the data for n equals 13 had not been plotted on figure 4. Add a tick in each row of table 1 to identify the effect, if any, on the results you would obtain for Gmax, Gmin, lambda, and y. So we've got a table there with the options reduced, not affected, or increased. So let's go back to our graph and see what changes would take place. So we're looking to remove this result at a value of n equals 13, so it's the one on the far right. Now we can see there's one point that passes through the most extreme point, so it's dependent on that error bar, and that's going to be on the line Gmin. So if we take away that restriction caused by the point at n equals 13, then what we'll see is that actually Gmin would be able to be slightly shallower because it would then rest on the bottom of a lower error bar. So the gradient of Gmin would actually be reduced. So we're doing this in a funny order, but that's okay. What you might have noticed from that point as well is that the line Gmax is not dependent on that error bar because it doesn't actually pass through the top of the error bar, so that would be unaffected as well. We're then left with the values of lambda and y, which as you can see are dependent on Gmax and Gmin. Going back to our calculations that we used to obtain lambda and y, lambda, or the wavelength, is calculated as the average of Gmax and Gmin. And if one of those values is made smaller, it's going to bring down the average or the mean value, so lambda will be reduced. And then for the value of y, we need to look back at the graph. If the point at n equals 13 is removed, as we said before, the value of Gmin is going to decrease. The line will become shallower, but it will revolve around the highest point on the value at n equals 5. So if Gmin becomes smaller while the line still revolves around that top point, then it's going to hit the y-axis at a higher value. So our y-intercept of the Gmin line is going to be above 1.275, and that's going to bring the mean value of the y-intercept up that we calculated in the previous question. So the value of y is going to increase. So those are our 4 selections, each one with a mark, so 4 marks. A signal generator is connected to an oscilloscope as shown in figure 5. We've got figure 5 here, which shows a series circuit with a switch, a signal generator, and then the symbol for an oscilloscope. The Y voltage gain and the time-based settings of the oscilloscope are shown in figure 6. We've got the volts per division, which on our oscilloscope graph, as it were, are going to represent the y-axis, and then we've got the time division, which is going to be on the x-axis. So you can see the volts per division is set to 1 volt. So each square on the grid that we'll look at in a second will be 1 volt high, and then the time division is going to be on 0.5 milliseconds, so 5 times 10 to the minus 4 seconds width for each square on the grid. When switch S is open or off, the oscilloscope displays the waveform shown in figure 7. When S is closed or on, the oscilloscope displays the waveform shown in figure 8. Determine the peak-to-peak voltage V of the waveform shown in figure 8. So let's go to figure 8. Now, as we mentioned before, each square on this grid is going to be 1 volt high. So if we just add in a few of those markings on the axes just to remind ourselves where we are. So what you'll notice is that this graph has a minimum value of -3 volts. And if you look really closely, you can see that it goes up to 3.3 volts in the positive direction. So the difference between the bottom and the top is going to be 6.3 volts, and that is the peak-to-peak voltage. So let's write that in our answer space. So I've just written there the working that we would use to find this. So it's the difference between the positive and the negative. So between plus 3.3 and -3, it gives us a difference of 6.3 volts, which we just write into that space. So nice, easy first mark. Determine the frequency f of the waveform shown in figure 8. Let's look back at that graph again. Now this time we need to use the time base. So we need to know the width of the squares, if I just write those on. So if we look at a complete cycle of oscillation here, we could go from minus 1.9, where it starts to drop from the top, and the next point where it starts to drop from the top, which is going to be at 2.1. So we've got a difference there of 4 seconds. So that's our time period. And don't forget that's in milliseconds. So that's 1,000th of a second. We then want to find the frequency, which is the inverse of that number. So it's 1 divided by that time period. So let's write that in our answer space. So 250 Hertz there. Our first mark is going to be for correctly identifying the time period, and our second mark is going to be for correctly calculating the answer of 250 Hertz. So 2 marks there. Figure 9 shows the signal generator connected in series with a resistor R and a capacitor C. And you can see figure 9 there with a capacitor-resistor circuit. So as that signal generator oscillates, we're going to be charging that capacitor and discharging that capacitor through the resistor. The oscilloscope is connected across the capacitor. The Y voltage gain and time base settings are still the same as shown in figure 6. When S is closed or on, the oscilloscope displays the waveform shown in figure 10. So let's have a look at figure 10. So you can see it looks very similar to the graph we looked at before, but it's not as sharp. You can see there are these curves as it moves from 6.3 down to -3. There's kind of a curving off rather than a sharp square wave. Determine the time constant of the circuit in figure 9. So let's look back at our graph. Now the trick to start with on this kind of graph is to identify a capacitor voltage decay graph shape. So let's identify a period of time where that takes place. So if we treat this like a capacitor decay graph starting at 6.3 volts and going down to what we could call 0, let's identify a point where we can record a time and a change in voltage. So the point I've selected is where this marking X is, and that's at a voltage which is 0.5 volts above the minimum, so technically at -2.5 volts, and the time is 6 milliseconds from where the graph started to drop, because it's just over 1 square. So writing down the equation for voltage decay in a capacitor-resistor circuit in the answer space, the time constant of this circuit is going to be equal to CR. So let's make a substitution so that we don't have to keep writing CR every time. Let's rearrange to make tau, or the time constant, the subject. Now here we've had to use natural logs because we're finding the reverse function or the inverse function of an exponential. But if we substitute the values that we obtained into this equation, we should get the correct answer. So remember we had a time difference of 0.6 milliseconds. And then the voltage we could think of as changing between 6.3 and 0.5. So putting all of that into a calculator gives us 2.37 times 10 to the -4. And that's going to be a value in seconds. So in this question, your first mark is going to be for correctly identifying values and substituting them, and your second mark is going to be for getting the correct answer. What I'll do is I'll write down the values that I've obtained on the graph. So imagining this as a graph with a clear defined origin, you can see that the top, where it starts to drop, is at 6.3 volts. The point I've identified is at 0.6 milliseconds across and 0.5 volts up. So those are the values that I can then substitute in. So 2 marks for that question. A student suggests that setting the time base to 0.2 milliseconds per division might reduce uncertainty in the determination of the time constant. State and explain any possible advantage or disadvantage in making the suggested adjustment. Now, the first thing to say for this question would be that decreasing the time base from 0.5 milliseconds per division to 0.2 milliseconds per division will stretch the graph horizontally, because now each entire square represents a smaller time period. And that would be our first mark. The next thing to include would be some kind of quantitative change, i.e. by what factor would that stretch be? So if we're going from 0.5 to 0.2, then we've got to change by a factor of 2.5. That's our second mark. The third mark would be to comment on what that does to the resolution of the screen. Because we're technically zoomed in, we will have a higher resolution on that x-axis measurement. So we need to say that the resolution of the time axis has increased. So I just included the X there because it's the X-axis, and that will be your third mark. So 3 marks there. The student connects an identical resistor in parallel with R and uses the oscilloscope to display the waveform across C. Draw on figure 11 the waveform you expect the student to see. The waveform of figure 10 is shown as a dashed line to help you show how the waveform changes. The bit to focus in on to begin with is that an identical resistor is connected in parallel. So let's just make that change on the diagram. Now the resistor will be added in here. You don't need to include that to obtain a mark, but it's worth just showing where that is to see how the resistance changes. Now, when we have two resistors in parallel that are identical, their overall resistance will be half of one of those resistors on its own. Now, you could use the resistor combination equation, and since R1 and R2 are equal, let's call them R subscript I to show that they are individual identical resistors. We can then simplify this and then rearrange to get an expression for the total resistance, thus showing that the total resistance is a half of one of those individual resistors. So with that in mind, we're going to decrease the time constant because of that equation. Time constant equals capacitance multiplied by resistance. Now, it's not important for us to know that the time constant halves, we just need to know that it decreases so that we know what to do to the shape of the graph. Now, this is obviously judged by I, so we don't need to do an exact time constant decrease by a factor of 2, but we need to show what the shape of that graph would be if the time constant were to decrease. So we've got the same maximum and minimum values that the voltage reaches, but for example, on this decline, it would reach the lower voltages much more quickly. So the graph would curve off more steeply and reach the minimum value much more quickly. Now, the same thing happens when the voltage increases. Whether we're charging or discharging, the process is quickened by a reduced time constant. Now, you don't need to show this second curve to get the graph mark, but if you do show it, you have to show it correctly because you could actually get that mark removed if it's incorrect. So for sake of completion, let's just do the same again for that last part of the graph because it repeats from the first curve that we did. So that would be your first mark. Your second mark would be to explain the change in the waveform. So it's basically what we've just described and what I've explained next to the diagram. So we're halving the overall resistance, and then we're saying that that causes the time constant to halve also. Now, technically, you don't need to say that the time constant halves, but you do need to say that the resistance halves, and then it's implied that that would also cause the time constant to halve. So that's your second mark, so 2 marks there. Figure 12a is a graph of voltage against time, showing the output of the signal generator. Figure 12b shows the voltage across C during the same time interval. The student interchanges the positions of R and C and connects the oscilloscope across R. Complete figure 12c to draw the voltage across R during the time interval. Now, this is a 2-mark question. So we've got figure 12a, which just shows that signal generator square wave output, as we've seen before. Figure 12b shows the voltage time graph across the capacitor. So you've got those curved edges there because it's discharging and charging through the resistor. Now, what we need to draw is the voltage time graph across R. Now, the thing to apply here in this circuit is Kirchhoff's second law, which tells us that the sum of the EMFs in a closed loop is equal to the sum of the PDs, or the sum of the electromotive forces in a closed loop is equal to the sum of the potential differences in that closed loop. Now, what you'll find is that this signal generator is being used to charge the capacitor, and then it's also discharging. So what we can do is superpose these two graphs on top of each other, but remember that they're in opposite directions because one is an EMF, it's a supply. The other one is what's thought of as a potential difference. This is why we have a positive and a negative region on this graph, because the potential difference across the resistor represents the difference in potential difference between the other two components. So to start with, the graph in figure 12c will be at 0 because the potential difference across the signal generator is positive V, and the potential difference across the capacitor is V, but it's in the other direction. What then happens is that the signal generator immediately drops to 0 but the capacitor is on a delay and doesn't return to 0 as quickly. So in that split second where figure 12a drops to 0, figure 12b is more or less still at V in the opposite direction. So there's a huge sudden jump in potential difference across the resistor. Now you don't need to include that vertical line to obtain marks, but it's worth including just to show the overall shape of the graph. Now by the time we get to the next vertical dotted line, both graphs must have returned to opposite values. So by the time we get to that next dotted line, both graphs will have returned to 0. But the difference in potential difference between the other two components curves towards 0 as there's a delay. Now you don't need to get the shape of this graph perfect, but you do need to show that it's not a sudden change, it's a gradual change. Now the reverse of the previous process occurs and there's a sudden jump again, but this time in the positive direction, as the signal generator suddenly jumps up to positive V, but the capacitor takes time to drop to negative V because of the resistor. Now again, by the time we reach the next vertical dotted line, both graphs have returned to equal and opposite values. Now this is one full cycle of the graph, so the same thing just happens again, you just need to continue that shape. So the first mark here of the two is going to be for obtaining the correct negative region of the graph, and the second mark is going to be for obtaining the correct shape of the positive region. So you need to have those curved lines in the correct direction. So 2 marks there. State and explain what changes, if any, the student needs to make to the settings of the oscilloscope so the waveform across R is fully displayed. Now we've just seen the waveform across R and it looks slightly different to the waveforms across the signal generator and the capacitor. So let's take another look. Now if we picture that this is taking place on an oscilloscope screen, that screen will need to include both the positive and the negative potential difference values up to the value of V that was stated before. So where we previously got away with including just V and 0 as maximum and minimum values, this time we need to go right the way from V down to negative V. So you could say that we need to zoom out on this graph. Now there are several ways to describe that change. One would be to reduce the gain, the other would be to increase the number of volts per division, but both are fine. So that would be your first mark. The other thing to note is that at the center of this oscilloscope screen, we've got a voltage of 0, not a voltage of presumably half of V. So we're going to need to move this screen vertically to include both the positive and the negative V values, so adjusting the Y shift. And that's going to be your second mark. So the first mark for effectively zooming out on the vertical axis, and the second mark for moving up and down, adjusting the Y, the vertical shift. So 2 marks there. This question is about an experiment with a linear air track. The block is used to raise one end of the track. A bumper fitted with a rubber cord is attached at the lower end of the track. The air track has a length of 2 meters and there is a scale with major divisions marked in centimeters along the side. The 0 of the scale is at the lower end, as shown in figure 13. So we can see that that rubber cord from above, so it's kind of a top-down view. You can then see the side view of the track, which is raised on one side to create a slope. Those grey rectangles represent 10 centimeter markings. A glider is placed in contact with the rubber cord on the bumper at the lower end of the track. The position of the glider relative to the fixed scale can be determined using figure 14. So we've got figure 14 there, and you can see that the front end, so the end of the glider that's highest up, is currently at 23.8 centimeters. That's going to come in useful later. The glider is then moved to the position shown in figure 15. Now you can see there isn't a grey rectangle there with a 10 centimeter marking, but we know that this is right up at the end of the 2 meter air track. So this position here is going to be at 198.4 centimeters, because you can see that the corner, the front corner, is at the 8.4 centimeter mark of that 10 centimeter division. The air supply to the track is turned on and the glider is released. The glider accelerates down the track, strikes the rubber cord on the bumper, and rebounds back up the track. The glider is allowed to bounce off the rubber band 20 times before it is stopped. A student reads and records the highest position P of the glider after each rebound N. Some of the student's data are shown in Table 2. Additional columns have been provided to allow you to complete question 3.2 and question 3.3. So we've got Table 2 here with a missing value of P at n equals 0, and then we've got x values and then the natural log of those x values. The value of P corresponding to n equals 0 is the glider's initial position at the top of the track. Deduce this value of P using figure 13 and figure 15. Write this result in Table 2. So if we go back to figure 13 and figure 15, so first of all on figure 13, we can see that the detail of scale at the upper end of the track is that the top end is going to be 190 centimeters. So we're going to combine that with our findings from figure 15. And as we said before, that position is going to be at 198.4 centimeters. So the value of P at n equals 0 is going to be 198.4 centimeters, and this is the only value that you can obtain. There's no range within which the value could fall. It has to be 198.4 centimeters. As it travels from the lower end of the track to each position P, the glider moves through a distance x. Deduce x for all the values of n using figure 14. Write these results in Table 2. So as we can see in figure 14, the lowest position that the higher end of the glider can reach is 23.8 centimeters. So all distances fallen are calculated from the position at the top end of the glider with 23.8 centimeters subtracted. So going back to this table, all we need to do is subtract 23.8 centimeters from each P value. So if you've correctly made all of those subtractions, that's your mark. Plot on figure 16 a graph of ln x, or the natural log of x, against n. Record your values of ln x in Table 2. So this is a 3-mark question. We need to first of all make sure that we calculate those values correctly. So using a calculator, find the natural log of all of those x values. So your first mark for that question will be for correctly calculating the natural log values. So I just recorded that here. Second and third mark are going to be for correctly plotting the graph. So in more detail, the second mark is going to be obtained by labeling the y-axis as natural log of x in centimeters, as it's described in that column of the table. But to secure that second mark, you need to have a suitable scale which uses up more than half of the graph and has a consistent interval. So I would recommend starting at 3 and then having major divisions of 0.2. Your third mark is going to be for plotting the points correctly. Your third mark is going to be for plotting the points correctly and drawing a line of best fit, which, as you can see from the table, needs to have a negative gradient. So as you can see, I've plotted those points correctly, and I've drawn a line of best fit through all of those points. So that would be your third mark. Explain why the graph you plotted confirms that x decreases exponentially with n. Now, in short, the answer is that the graph is linear and it has a negative gradient. But if we look at the equation of a straight line and apply it to the values that we have, so the x values here are n and the y values here are the natural log of x. And of course here m and c are the gradients and the y-intercepts respectively. We're keeping those the same. They will be constant because it's a straight line graph. If we then rearrange this to make x the subject, we should first of all make both sides powers of e. Now, e to the power of ln x is just going to be x. And because we've got mn plus c in that power, we can separate that into 2 separate e functions. Now that tells half the story, but it doesn't yet recognize why x decreases exponentially with n. Well, looking back at the graph, we can see that the straight line has a negative gradient. So m will be a negative value. And if m, the gradient, is negative, then we're saying that x is equal to some constant e to the c multiplied by an e to a negative number times n. So the fact that an increasing n is in a negative power of the exponential function, we can say that x is decreasing exponentially with n. So going back to my shortened answer, the graph is linear and it has a negative gradient. And that's going to be your mark. You do need to mention the linear nature and the negative gradient nature of the graph to get that mark. Determine, using your graph in figure 16, the value of x when n is 20. So let's go back to our graph. The trick here is to make the line we have so far into a triangle so that we can then extrapolate the graph onward to find out where it would reach on the vertical axis when the n value is 20. So we know that this point in the bottom right of the triangle is about 3.4. We don't know that it's exactly 3.401 as stated in the table because remember we're relying on the line of best fit, not the point itself. The base width of this triangle is going to be 13 and the height of the triangle is going to be equal to the difference between 5.16 and 3.4. So what we need to do is extrapolate that line down until the triangle has a width of 20 and see what the value of ln x will then be so that we can calculate the value of x itself. So showing this on a diagram, I've included a scale all the way down to 0 now. Obviously this isn't the scale. So this shows our line in the overall scale from 0 to 5.16 and it only moves across to 13. So if we continue this along, we want the value at 20. Now, as I said, this isn't the scale. As you can see, that 13 isn't where it should be in relation to the 20, but it's just a visualization. So the first thing to say is that the width of the triangle increases by a factor of 20 over 13. Now, using the similar triangles method, we can say that the height of the triangle increases by this also. So I've called this new height of the triangle h nu, which is going to be 20 over 13 times the height of the original triangle. Now bear in mind that that gives us the height of the triangle, not the value on the y-axis. So what we need to do is subtract this h nu value from 5.16 to find the y-axis value at which this 20 width occurs. Now what we can do is rearrange this equation to make x the subject and then it will tell us that value directly. So we end up with a value of 11.62 centimeters. So let's round that to 11.6. Now this is a 3-mark question. So the first mark is going to be for correctly reading off the values in the first triangle. The second mark is going to be for correctly identifying the scale to which the base of the triangle increases. Alternately, if you've used the gradient of the line to find this new point where x is equal to 20, then that would be where that mark is obtained, is for finding the gradient of the graph. And then finally, the third mark is for getting a correct value in the range between 10.8 and 12.7 centimeters. So 3 marks there. Describe and explain 2 procedures the student should take to reduce uncertainty in the measurements of P. So this is a 4-mark question. We'll get 2 marks for the first procedure and 2 marks for the second. It's a describe and explain question. So for each procedure, you'll get 1 mark for describing and 1 mark for explaining. So the first procedure could be to repeat the experiment and calculate a mean value. And the reason for this would be to reduce the effect of random or human error. Now the second procedure, again, you can say to repeat the experiment, but this is for a different purpose, and that is to look out for anomalies. And the reason we want to do this is so that we can then discard those anomalous results if they don't fit the general trend in the data. So as explained before, you get 1 mark for describing the procedure and another for explaining. There are other procedures that you could mention, for example, viewing the air track at right angles to reduce what we call parallax error, a bit like when you're looking at a thermometer reading or a test tube. You want to be level with the surface of the liquid so that you're reading the scale behind it or in front of it correctly. What you might also want to do is to switch the air track around its direction and repeat the experiment again, just in case there's an imbalance in the table or the desk that you're using, and then find an average between your values in either direction. You could also talk about the use of video technology so that you can slow down video footage and record more precisely the level where the glider reaches each time. But these 2 procedures are fine. We've got 4 points made, so 4 marks.